Hey, welcome. Um, so my name is Stepan Paul. I'm the chair of the Undergraduate Events Committee in the Math Department here at Harvard. Um, and this talk is part of the Why Do Math series, which is a joint effort by the Math Department and the Science Research Public Lectures. I won't try to address the titular title of the series, but let me address a more narrow topic, which is why do math? Why did we title this, and what were we trying to get at with the title? So we say, why do math? First of all, to be shamelessly provocative, but also we have a lot of undergraduates who might just take one or two classes in our department and then go on to other fields. And this series was born out of a desire to enrich their mathematical experiences here at Harvard by having some great speakers come, share their research, share their experience, and expose other facets of mathematics. So we're going to have undergraduate Vaughn McDonald come introduce the speaker.
Sorry. It is my pleasure to introduce Kurt McMullen to the Why Do Math series. He is the Maria Moores Cabot Professor of Math and the current department chair here at Harvard. His research focuses on complex dynamics, hyperbolic geometry, and Teichmuller theory. As an example of one of his earlier results, he proved that one can solve the quintic equation by iteration of rational maps. For his work, he has received numerous distinctions, including the 1991 Salem Prize, and in 1998, he received the Fields Medal. Professor McMullen also teaches some wonderful undergraduate classes here, or graduate classes, one of which was the Riemann surfaces class I actually just took.
He's getting an A.
And today he'll be talking about a skeptical history of numbers. So please join me in welcoming Professor McMullen.
So thank you very much, Vaughn, and especially I want to thank Stepan for all the work he's done on this new program of undergraduate activities and public activities related to mathematics here at Harvard. We're really trying to emphasize that mathematics is a fascinating, inclusive, and welcoming topic. And I'm pleased to be a part of this series. So here's what I want to talk about today. Quantum theory, virtual particles, curved space, and dark energy all emerged from a critical assessment of the foundation of physics in the 20th century. In the same period, perhaps less well known, a foundational crisis threatened the edifice of mathematics itself. So focusing on the concept of numbers, this talk will recap some of the great leaps of imagination in the history of mathematical thought. It will describe this foundational crisis, critique the attempts to rescue certainty in mathematics, and assess the current state of affairs. So the first thing I want to draw your attention to is the fact that mathematics is a human construction of enormous richness and complexity that has been built by thousands and thousands of minds over thousands and thousands of years. It is perhaps the highest intellectual endeavor in terms of the amount of sustained thought carried out over time that human beings have accomplished. And of course, this is accomplished by the miracle of language, that we have this enormous tower of mathematical results and mathematical thought. Often in the Science Center lecture series, you'll hear about sort of the last brick that was added to the top of the pyramid. But what I want to do today is try to look at the pyramid itself, which is often neglected. And it's partly neglected because tremendous mathematical breakthroughs become mundane over time and are taught in elementary school and high school and even become drudgery. And they deserve to be seen sometimes with fresh eyes. And number is a good example of this. So let me start by asking, what is a number? So this is how I learned what a number was. I had to do this kind of problem in my workbook. And I think what I was supposed to do was cut out these rectangles and match them with the fruit collections above. But what is a number? So I asked this in one of my undergraduate classes a few years ago, and I got a very good answer. The number 3 is 3 fire trucks without the fire truck. It's an abstraction of the notion of counting. And that's already in itself a remarkable idea. Now, once we have the ordinary counting numbers, 0, 1, 2, 3, and so on, which we learn in grade school, in a little more advanced class, you learn to add in some negative numbers. And then, of course, it's useful to take fractions, 22/7, 94/100, even negative fractions. Those give what are called the rational numbers. And what really gave birth to these numbers, including the negative numbers and the fractions, was the desire to solve linear equations. That is, I have an equation of the form ax plus b equals 0. I know what a and b are. I want to solve what x is. I have 7 oranges to divide among 3 people. How should I partition them out? That's a problem that you can solve using rational numbers. The answer is 7/3, or 2 1/3 to each person. Okay, so what came after these whole numbers was again motivated by algebra. And the next simplest equation you might solve is called the quadratic equation. It's an equation in which the square of a number appears, here ax squared. And again, one learns in school that there's some formula for the solution, some complicated thing. But the main thing is that the formula involves a square root. And the study of these quadratic equations goes back a long time, at least to, in written works, to Diophantus in around 200 AD, who considered in kind of word form many quadratic equations. But really the big advance in quadratic equations was due to Al-Khwarizmi, a Persian mathematician from the 800s, who gave a systematic account of how to solve these equations by what we now call completing the square. And in fact, the title of his work includes the word algebra, from which we get the word algebra, and this means completing, as in the process that we now use for solving quadratic equations. And the great fact about these numbers is that although they are irrational, these square roots, they cannot be expressed as simple fractions in general. Square root of 2 is not equal to 3/2 or anything else. It's kind of a new kind of number in its own right. It's not rational, therefore it's called irrational. These irrational numbers allow us to solve simple quadratic equations. But once we have them, we can start using them in combination with our arithmetic operations as well. We can start taking all sorts of fractional powers of numbers. We can add the results together. And doing this, we can solve a lot more equations. For example, we can solve the equation x cubed equals x plus 1. The solution is, well, this. So it's a complicated expression. It involves nested radicals. And curiously, the numbers 69 and 18 are coming in here. But nevertheless, once we have these, they are a powerful tool for solving equations. Now, historically, the quadratic equations were solved in antiquity. In fact, it's now believed, based on the cuneiform texts, a fragment of which I reproduce here, that quadratic equations were known, solutions were known as long as 2000 BC. However, the solutions to the cubic and quartic equations of degree 3 and 4, had to wait until the Italians in the 1500s. And I'd like to mention that even 230 years later, in 1735, here is what Isaac Barrow wrote in his mathematical lectures concerning square roots, which were called surds at the time. He said, now, as to what pertains to these surd numbers, which, as it were by way of reproach and calumny, have no merit of their own, are also styled irrational, irregular, and inexplicable, They are by many denied to be numbers properly speaking, and are wont to be banished from arithmetic to another science, which is yet no science, namely algebra. So there was already some skepticism, even in the 1700s, about the idea of, say, cube roots of numbers. Okay, now there's another source of numbers beyond counting numbers and equations, which is geometry. Before I get to that, let me say one more thing about polynomials. What about fifth degree polynomials, like solving this equation, x to the fifth equals x plus 1? Well, it turns out that in the 1800s, it was shown that there's no expression for the solution to this equation involving square roots or fifth roots or any kind of roots. The new algebraic operations we've introduced already break down when we try to solve fifth degree equations. And just to follow up on what Vaughn mentioned in the introduction, there's a reason for this, which is that a fifth degree equation generally has 5 roots. And you're going to write down one of the roots. Which one are you going to write down? You have to somehow break the symmetry of the equation, and that's hard to do. That's really the challenge, is figuring out how to distinguish one root from all the rest. So around 2000 AD, Peter Doyle and I found a new way to solve the quintic equation. And to make a long story short, there's this beautiful sort of fractal soccer ball, and the way you solve your quintic equation is you pick a point at random on this sphere, and then the color of the region that you've chosen determines which root of the fifth degree polynomial will come out of the process. So going back to this equation, one of the roots turns out to be this number, which, although we can't express it in terms of square roots, we can express it in terms of decimals. You could type this into your calculator, and it will quickly print out a result like this, or into your computer, and it will print out thousands of digits of accuracy for this result. But what is this object anyway? This is some new kind of number. It's not a square root. It's not a whole number. It's not a rational number. It just keeps going on forever. Well, this kind of number has its origins in not algebra, but geometry. So geometry is the study of shape. And I go back again to our grade school introduction to this field. And one of the interesting questions in geometry is, like the question of numbers, what is geometry about? So one answer to this, going back to the Greek philosophers, is that geometry is about abstract shapes, which exist in some nether world of Platonic ideals where everything is exact. And in our impoverished real world, we see things like salt crystals or Amazon boxes that are approximately in the shape of cubes. But there is no real cube in nature. We only see shadows of these ideals. And the ideals, a beautiful example of these ideal shapes are these 5 Platonic solids. These are the 5 most symmetric shapes that you can build as polyhedra. And the most famous of them is the dodecahedron here. It's a 12-sided figure. And the construction of this figure is very subtle. It was reputedly known and kept secret by the Pythagoreans, who banished from one of the members of their school, Hypasus, for revealing the construction of the dodecahedron and actually for claiming it as his own. But actually, there's a compelling variant of this story, which says that Hypasus was not expelled, he was drowned at sea. And it wasn't for revealing the construction of the dodecahedron, it was for revealing a far more revolutionary discovery, namely the existence of irrational numbers. And notice, by the way, that even the idea of an irrational number only makes sense in a Platonic world where you can have exact numbers, where you can tell the difference between an irrational and a very close rational approximation. Okay, so these numbers that arise as lengths in geometry, they're what are called now the real numbers. And they include the square root of 2, but they also include various ratios between shapes in this pentagram. They include a number like pi, which has to do with the circumference and diameter of a circle. It can be written to a couple of tens or 20s or to billions of decimal places by current computation. And basically, the real numbers are a geometrical concept. They form a continuum. They describe all of the points on the line that's drawn here, and they interpolate between the whole numbers and make them into a connected realm. That's really what the real numbers are for. They are a manifestation of geometry per se, and we represent them by decimals in modern life, but a typical real number has a decimal expansion like that of pi. It goes on forever. To have the exact representation of a real number, you'd have to have an infinite list of digits. And this idea of real numbers is pretty much all you need in life. We pretty much have finished our story. We've caught up to the modern day, except for one thing, which is if you're going to have real numbers, you must have something else, namely imaginary numbers. Now, what are imaginary numbers for? Well, it turns out there's some things you just can't find the square root of. And one of them is -1. So we can find the square root of 2. On the real line, it's a little bit past 1, a little bit less than 2, a little bit bigger than 1. But if we try to find a number whose square is -1, we're in trouble. For example, if we square -1, it turns out we get 1. And in fact, if we square any negative number, we get a positive number. So who is ever going to square over to get -1? And the answer is nobody. You're looking in the wrong place. The square root of -1 is not on the real line. It goes up here. It should be placed in the vertical direction, not in the horizontal direction, and at distance 1 from the origin and making a 90-degree angle with the real numbers. Now, why this strange geometrical picture of this missing number in our arithmetic? The reason the square root of 1 goes here is because when you pass to the complex numbers, that is, when you include the imaginary numbers in your arithmetic, you find that when you square a number, its angle doubles. So here, the angle that square root of -1 makes with the real axis is 90 degrees. When you square it, it goes over to -1. And so this is the appropriate place to put this imaginary number. And the motivation, again, to add this number in was to find solutions to equations like x squared equals -1 that otherwise didn't have solutions. Well, now we really are done, because there's a famous mathematical result that says every polynomial can be solved using complex numbers. This is such an important result, it's called the fundamental theorem of algebra. It was proved by one of the greatest mathematicians of all time, Gauss, in 1799. But remarkably, to modern mathematicians, the proof of this theorem, which as you can see took an additional 300 years after solving the cubic equations and the quartic equations to figure out that complex numbers could solve any equations. The proof of this to modern mathematicians can be summed up very easily. It looks like this. Okay, any questions? So let me explain why this idea of syrup pouring over a stack of pancakes is the way modern mathematicians visualize the proof of the fundamental theorem of algebra. So here's our problem. We have a polynomial, and we're going to plug a complex number into it. I'm going to call the complex number z. We plug it into the number, we get a new number, p of z. Now remember, complex numbers form a plane. So I'm going to take some points in the plane here on the left, and when I plug them into a polynomial, I'll get some new points on the right. And all I want to do is show that there's some point on the left which comes over and hits 0 here. Because if some point here hits 0, that's a solution to the equation. I found a z you can plug into the polynomial, and it gives the answer 0. So what I'm going to do is I'm going to start spreading a round ball around the origin here. I'm going to make it bigger and bigger. And while we see that evolve, we'll also look at what its image is over here when you apply the mapping P. And if the image crosses this point, we've won. We've proved the polynomial has a root. So here we go. And that's that. So you see this expanding ball on the right has a complicated image at first, but it's more or less obvious that when it gets really big, it just covers everything on the other side like a spreading pool of syrup. And this is, in fact, a geometric proof of the fundamental theorem of algebra. OK, so algebra is over. What should we talk about next? Well, I'd like to go back to numbers. So let me mention a few more facts about numbers that show that there's still a lot of hard things to do with numbers once you've shown that polynomials have complex solutions. So one thing we can try to do in addition to solving these polynomials is we can try to solve whole number equations. So a typical whole number equation would be something like this. I want to find 3 numbers such that x squared plus y squared is equal to z squared. And this equation is the Pythagorean equation. If you can find a solution to this, then these are the lengths of the sides of a right triangle. And an example of a solution is, well, it turns out 5 squared plus 12 squared is 13 squared. Great. So this kind of equation with only 2's in the exponents turns out to have a lot of solutions, and they can be found somewhat systematically. It was a huge breakthrough in our lifetimes when a 350-year-old problem of Fermat was solved by showing that there are no interesting solutions to the same equation if you change 2 to 4, or in fact to any other number that's bigger than 3. So the only solutions to this equation, if you put a large exponent in here, are boring, something like 0 plus 1 is equal to 1. But aside from that, there's essentially no solutions, and that was a very deep mathematical development taking several hundred years and culminating in Andrew Weil's proof of this famous Fermat's last theorem in our lifetime. And then there's an intermediate case. I skipped over n is equal to 3. It turns out that when you have cubic equations, that sometimes there are solutions, like 5 squared is 3 cubed minus 2. And perhaps one of the most interesting developments is that we now know the theory of solutions of these equations is infinitely wrapped up with how these equations look over the complex numbers. If we look for complex roots of these equations instead of whole number roots, then we can make a geometric picture of the space of solutions. And it turns out that when the complex solutions form a sphere, there's lots of solutions. That's this first case. When they form a surface with many handles, then there's very few solutions, sometimes none. And when they form a torus with one hole, where it's a kind of intermediate case. Sometimes there's very few solutions, but also sometimes there's infinitely many. And the reason there's infinitely many is that in the case where there's one hole here, when you have this cubic equation, there's a procedure to start with one solution and generate more solutions. So for example, this equation also has a solution that looks like this. So I have to tell you why I wrote down this equation, which is that when I was in graduate school here at Harvard, the crank letters to the department, which consisted mostly of alleged proofs of Fermat's last theorem, were just left in the lounge for the graduate students to answer. And one of the graduate students noticed that the proof that had been sent in was claimed to be not only a proof that this equation has no solutions, but also that this equation has no solutions. And so what they did is they looked at this equation, they found this solution, and then they used it to generate this solution. And they wrote back to the letter writer and said, thank you for your interesting letter and your proof of Fermat's last theorem, but I couldn't help noticing your last theorem doesn't seem to be right because the following solution immediately came to mind. So that's one way to deal with incoming mail. Okay, so I'd like to move now away from even the theory of equations and just talk about numbers. In fact, I'm going to talk mostly about whole numbers for the rest of the talk. So let's talk about large numbers. So I wrote down some numbers with many digits, but what about just large whole numbers? Well, one of the reasons we use Arabic numerals now, as well as exponential notation, is that in Roman numerals, it's hard to write very big numbers. In fact, according to some sources, this is the largest number you can write in Roman numerals. It's barely 4,000. So you can't even discuss the population of a city using Roman numerals. And this was taken up by Archimedes as a challenge in 250 BC. And he wrote a work called the Sand Reckoner, in which he vastly extended the size of numbers available to the imagination. And what he did is he introduced a number called a myriad, and then he was able to then talk about myriads of myriads and myriads of myriads of myriads. And let me just read you a little bit about what he wrote to his ruler. He said, "There are some, King Gelon, who think that the number of the sand is infinite in multitude." Think how contrary that is to modern thought, but yes, there's infinitely many grains of sand in the world. And I mean by that the sand not only in that region which exists about Syracuse and the rest of Sicily, but also that which is found in every region, whether inhabited or uninhabited. But I will try to show you by means of geometrical proofs, which you will be able to follow, that of the numbers named by me, some exceed not only the number of the mass of sand equal in magnitude to the earth filled up with sand, but also that of the mass equal in magnitude to the universe. So by introducing these numbers, Archimedes was basically able to talk about what we would nowadays write in exponential notation, and he estimated that it takes about 10 to the 63 grains of sand to fill the entire universe. And interestingly, this is not so far off from the current estimate of the number of atoms in the observable universe. So he was grappling with the same scale of numbers that we now do in cosmology and physics. Now, can one really apprehend a number like this, 1 with 63 zeros after it? Well, I think in the space age, when I grew up, it actually became fairly easy to imagine what very large numbers look like. And this is illustrated in a famous movie of the Eames called Powers of 10. So I'll just show you an excerpt from this, and you'll be able to visualize the number 10 to the 14 by watching this movie. Okay, so here we are. We're 100 million meters away from Chicago. And now we're going to zoom in. Solar system.
10 to the 9th meters, 10 to the 8th, 7, 6, 5, 4, 3, 2, 1. We are back at our starting point. We slow up at 1 meter, 10 to the 0 power.
Okay, so physical reality easily accommodates numbers of the size like 10 to the 14. What about mathematics? Does mathematics have access to numbers that are larger than this, and does it need them? Well, one way to make even larger numbers in mathematics is by using towers. So let me just tell you what a tower is. The first tower is just the number 10. The second level tower is 10 to the 10th power. So that means one with 10 zeros, that's 10 billion. After that, we're going to go whipping past Google, which before it was a search engine, was a number, one followed by 100 zeros. And we're going to go up to a tower of 3 tens, 10 to the 10 to the 10. Now, what does that mean? It means a 1 followed by 10 billion zeros. See, 10 to the 10 was 10 billion. Now let's write down a number that has that many zeros. So this is an absolutely enormous number. And now what's 10t4? It's 10 to the 10 to the 10 to the 10. So it's the number of zeros in this number is given by this number. And by taking these stacks of 10 higher and higher and higher, we obtain absolutely enormous numbers, far beyond anything that's necessary or even possibly physically relevant in our current understanding of the universe. Nevertheless, numbers of this size occur in practice in mathematics. In fact, for a long time, the largest number considered interesting in mathematics was called Skew's number, which is 10 to the 10 to the 10 to the 34. And it was a bound for how the size of the first prime number where some inequality that's known to hold for small prime numbers reverses. And in 1933, Skew's proved that by the time you get up to primes of this size, you're going to see a reversal in this mathematical inequality. So as I said, this was for a long time adequate for not just physics, but all mathematical discussions. Well, no more. We now have access to and need larger numbers than these. So these are called wowzers. And they illustrate the untamed power of induction, of just taking a number you've got already and putting it into a machine to make an even bigger number, and then feeding that back into the same machine. So the first wowzer is 10. The second wowzer is a tower of height 10. Okay, so 10 to the 10 to the 10 to the 10. The third wowzer is a tower whose height is given by the second wowzer. So you take this unimaginably high number, and then you make a tower of tens that's higher than the number of molecules in the universe by an enormous factor. That's just W of 3. And then you keep going after that. So I hope I'm starting to give you just some sense for the enormous numbers that can be easily constructed and in fact come up these days in certain mathematical problems. However, even these are not close to the current record holder of interesting math numbers. The largest number to appear, as far as I know, in a serious mathematical journal is called Graham's number, G. And I can give you a hint of what this number is about. It's very hard to say how big it is, but it's much bigger than anything we've talked about so far. Here's what it's for. There's a famous fact that if you invite 6 people to dinner, and they all have strong feelings about each other, you'll either find 3 mutual friends or 3 mutual enemies. There's just only so many possibilities. Well, Graham asked the following variant of this question: what if you invite 2 to the n people to dinner, and you put them at the vertices of an n-dimensional cube? Then how big does the cube have to be so that you can find 4 mutual friends or 4 mutual enemies that lie in what's called a plane, which is a subset of this very complicated cube where they, so to speak, differ by changing only one coordinate at a time. So here's 4 mutual friends. Here's 4, if this were blue, they would be 4 mutual enemies. But maybe, depending on the relationships, you can't find a plane in which you have this. Well, then make the number of people invited to dinner bigger. And so Graham's number was an estimate for how big this cube has to be before you can be certain there will be either a red square or a blue square. And this was formulated in 1977. Now, before you get too excited about Graham's number, you might ask, Graham proved that if you invite this many people, then you're guaranteed to have this kind of configuration. Can you get away with fewer? In other words, what's the lower bound on this number n? Is it possible we could take n smaller than, say, Wowzer of 3 or Wowzer of 2? Well, the known lower bound is 12. So in some sense, Graham's number measures the size of our ignorance. It is nevertheless the largest number that I think has appeared in a serious mathematical discussion. Okay. Even so, there are procedures for producing numbers that are even larger than this. And one famous one I just cannot avoid mentioning is called the busy beaver function. This is like the towers or the Wowzers, but it turns out it grows faster than anything that can possibly be computed. And the way this number works is the following. I have some personal experience with this because I used to work, had a summer job working with the printers attached to an IBM mainframe. And every once in a while, some computer program would go rogue, and it would start printing out pages and pages and pages of paper. Now, there were two possibilities. One is that the program has gone into an infinite loop, and it's just going to run forever. The other is that the program is meant to produce a lot of data, but it will eventually stop. So this number is defined as follows. It's the amount of output that you can get, a computer program of length n to produce. That's called B of n. So you can imagine a competition among undergraduates to write a very short program that makes a huge mess in the line printer. And what's remarkable is that this number grows very, very rapidly, but it's not even clear if it's defined. And this is a hint of something I'm going to come to at the end of the talk. Do numbers actually make sense? And the reason that there's some issue about whether or not this number makes sense is very simple. Suppose I start running a computer program and it starts producing a lot of paper, and somebody says, no, I'm pretty sure it's going to stop. And so I wait, and it doesn't stop. And I come back tomorrow, and it's still running. How can you ever know whether it's going to stop or not? That turns out to be a very difficult question to answer. It's called the halting problem. In fact, it turns out that's an impossible question to answer. So it's not even clear if this number makes sense. Okay, well, enough of large integers. Let's go all the way and look at infinity. So what about infinity? What is infinity anyway? Is there such a thing as infinity? Should we be concerned about it? Should we be skeptical about its existence? We can think about the infinitely large, but we can also think about the infinitely small. We can also think about infinitely many things that have to happen in a finite amount of time. So Zeno confronted the paradox of infinity in 430 BC, and he formulated the following well-known story of a race between the fleet-foot Achilles and the slow-foot tortoise. And so here's the race. Achilles runs up to where the tortoise was. He gives the tortoise a head start. So the tortoise starts here. Achilles runs up, reaches the starting line, has almost passed the tortoise. Oh, but the tortoise, in the meantime, has walked up to here. Oh, well. So Achilles catches up with where the tortoise was, but in the meantime, the tortoise has advanced a little bit more. Well, so he catches up to that, but still it advanced a little bit more in the meantime. And he catches up, and so he can never pass the tortoise, right? Because there's infinitely many things he has to do before we can even catch up to the tortoise, let alone pass it. That's a typical paradox of infinity. Now, let me flash forward roughly 2,000 years to Newton. So Newton would have no problem with the idea that Achilles is not quite passing the tortoise yet, but the difference between where he's standing and where the tortoise is infinitesimal. It's negligible, it doesn't count. And Newton used this idea of infinitesimals to invent calculus. And the way he used it is very simple. He said, let's suppose we have a particle moving around as a function of time. I want to know the speed at which the particle is moving. How do I figure out what the speed is? I ask where it is at time t, and then I let time advance by a very small amount, in fact, an infinitesimal amount, and I see how much the position of the particle changes. How much did the turtle move during time epsilon? And then I divide by epsilon, and that's the speed of motion. And if epsilon was like a minute, that would be only an approximation to the tortoise's speed. But if epsilon is infinitesimal, it gives me the speed exactly. This is how calculus was invented. And calculus is perhaps the most powerful and most significant discovery ever made in mathematics. All of our physical laws are formulated using the language of calculus. All models for the behavior of biological systems, chemical systems, even social and economic systems are based on differential equations, which ultimately are based on calculus. So this was a great thing that by taking the idea of the infinitely small seriously, Newton was able to revolutionize science. Here's what people thought about that. Here's George Berkeley talking about the infinitesimals. What are these same evanescent increments? They are neither finite quantities, nor quantities infinitely small, nor yet nothing. May we not call them the ghosts of departed quantities? So, remarkably, this extremely successful theory, which has been used to land men on the moon, is based on an idea that makes no sense. Now, mathematicians have figured out a way to make the idea make sense, and all calculus students learn to chant the following mantra. For every epsilon greater than or equal to 0, there exists a delta such that blah, 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 blah. And this is how you circumvent having to ever say the word infinitesimal. But all mathematicians, most mathematicians and all physicists think in terms of infinitesimals, and it's only when you're in polite society that you have to learn to chant this mantra. So it's really a kind of a paradoxical situation. Okay, I'd like to show another movie illustrating now not the powers of 10, but the number infinity. And this movie will be about a famous fractal, the Mandelbrot set. It'll be an analog of the Eames movie, and it'll only show it for a finite amount of time. But the point is that mathematical objects exist that are extremely complicated, and we can zoom into them as much as we want and just keep going and going, limited only by our patience and our computational power. So here's a picture of infinity. I'm zooming in at a point on the edge of the main cardioid of the Mandelbrot set. Now I'm going into the eye of an elephant, this is called. There's a kind of spiral. Let's look at one of those off-center elephants, maybe go into this strange region in the middle here, and lo and behold, we see another copy of the Mandelbrot set. And of course, we could continue now and choose an entirely different piece of this little Mandelbrot set inside the big one to zoom in on, and so on, and so on, and so on. You can find much better zooms, much longer zooms at higher resolution on the internet now. This is a rather dated movie made on my own desktop without too much work. But that gives you an idea of the fact that we really think of the infinite as existing in mathematics. Okay, now, here is the next revolution in our thinking about infinity. Let me give you an example of infinity. There's infinitely many whole numbers, 0, 1, 2, 3. It keeps going on forever. There's also infinitely many points on a straight line. So there's infinitely many real numbers. Well, it's now known that, in fact, there are more real numbers than there are integers, than there are whole numbers. And the number of whole numbers is basically the number of all possible books in the world, or the number of all possible sentences you could ever write down. Whereas the real numbers, this describes all of the possible points on a line. And it turns out there's more points on a line than all possible books in the world. And what that means is that when we draw this number line, we have some points on it that have names, 3, e, pi, square root of 2, but the vast majority of points on this line have no name. They cannot be described in words. That's one of the first hints that we're playing with paradox when we talk about the real numbers and large infinite sets. Well, it was George Cantor who discovered this, remarkable fact that there are at least 2 different sizes of infinity. In fact, he showed there's infinitely many different sizes of infinity, and that when we talk about collections of objects, like the collection of all natural numbers or all the points on the line, we're entering a world of enormous richness, which was called, by David Hilbert, Cantor's paradise. This idea that there was a calculus of infinity was, I think, unanticipated prior to the work of Cantor in the 1800s. And as I quote here, David Hilbert said, "No one shall expel us from the paradise that Cantor has created." And in fact, people tried, set to work on making very precise descriptions, mathematically precise descriptions of how you should talk about these different infinities in a logically correct way. And one of the first was this treatise by Gottlieb Frege. And just as this thesis on a formal language for pure thought, which was meant to allow one to discuss rigorously these infinite quantities, was about to go to press, he received a letter from Bertrand Russell, 1903, which showed him that the entire edifice that he constructed was, sorry to visit sand again, built on sand. It was as if he had uploaded Microsoft Windows and it just crashed. And he wrote, "Hardly anything more unfortunate can befall a scientific writer than to have one of the foundations of his edifice shaken after the work is finished." How did mathematicians start getting into trouble? Well, here's 2 ways of describing the crisis. So the first, I believe Russell learned from a librarian at Oxford named Barry, who thought this was just a kind of clever puzzle to pass around. Barry said, "Can you tell me the number n, which is the smallest positive integer not definable in fewer than 12 words?" Well, the thing is, this definition uses fewer than 12 words. So what could this number possibly be? Okay. Let's just hope we can't formulate that in mathematics. Then we don't have to worry about what this number is. Well, when you study set theory, there's something very similar that arises, and it arises because of the self-referential property that's in this sentence and the next one, which is called Russell's paradox. Russell said, okay, if we are allowed to have sets of things, let's look at all sets which don't contain themselves. Now, is this set a member of itself? Well, if it is a member of itself, then it must qualify by not being a member of itself. But if it's not a member of itself, then it has to be included in the set. Does it even make sense to write down this sentence in mathematics? And Frege had allowed one to write sentences like this. Okay, now you might say there's a pretty simple solution to this. Just don't allow sets to ever contain themselves. Okay, what about the set of all sets? How can that not contain itself? It's the set of all sets. So there's no simple solution to this problem. And I want to remark that just as mathematics was entering this crisis, all sorts of other related crises or shifts of perspective were happening across the world and in other disciplines. For example, up until this time, people had this very neat picture of the atom. It's just a little solar system. There's a nucleus and electrons going around. No. It turns out that experiments showed that it couldn't possibly be right. And in fact, maybe it doesn't even make sense to talk about where these electrons are because there's no experiment that can test where an electron is in its orbit around an atom. And quantum mechanics was invented to resolve this observational paradox. And our modern picture of the atom, which appeared just in the same period, is that the electron doesn't know where it is. It lives in sort of a probability cloud around the nucleus. So these foundational crises were not isolated to mathematics. In fact, among the 20th century revolutions that were contemporaneous with this mathematical crisis, there was the idea of replacing absolute space with relative space. The phrase everything is relative permeated all sorts of avenues of culture, not just physics. The solar system atom, as I just said, was replaced with the quantum atom. The faith in determinism was Laplace's idea that the universe is just clockwork, had to be replaced in light of quantum mechanics with an acceptance of uncertainty. And philosophically, positivism was replaced by things like existentialism. There were all sorts of revolutions happening at the same time. There was a general feeling that what we once felt was certain was now, on closer examination, subject to critique, and maybe even not as substantial as we thought. Okay, so let's solve this problem. So the first solution that was put forth in a 1,000-page treatise by Russell and Whitehead was, be very careful when you're defining A not to mention A. That turned out to be extremely awkward. Another solution that was put forward was, let's only talk about things that we really, really know are real. That is, that we can actually construct, like 7/3, but not the set of all sets. What does that even mean? That was called intuitionism. Unfortunately, that led to a theory of mathematics that was too impoverished to satisfy most people and to cover the kind of math that was being done up to that time. What won out was something called the axiomatic approach, which says we accept a small number of unassailable facts, and then you're not allowed to just talk about whatever you want to. You're only allowed to deduce conclusions that follow from these axioms. This was Hilbert's method, and it dominates mathematical thought to this day. Okay, so everything is fine. And in 1930, there was a conference in Königsberg. David Hilbert, who was retiring from his post at University of Göttingen, gave a famous speech in which he said, very optimistically, for us, there is no ignorabimus, and in my opinion, none whatever in natural science, meaning there's nothing that's unknowable. Wir müssen wissen, wir werden wissen. We must know, we will know. We have never found a problem in math that we couldn't solve. We will eventually solve them all. 3 days later at the same conference, Kurt Gödel announced his famous incompleteness theorem. He proved that mathematics is and will always be incomplete. And to go back a little to the historical context again, I just had to share this picture. So here's these two guys who were at the Institute for Advanced Study in Princeton, Einstein and Gödel, and they didn't get along with too many people except for each other. And one of them refused to accept the uncertainties of quantum mechanics. Einstein famously said, God does not play dice with the universe. And Gödel, on the other hand, proved the strongest version of the uncertainty principle, namely that mathematics will never answer all questions of math. That's what Gödel's incompleteness theorem says. There are some mathematical questions, maybe hard to say what, which we will never have the answer to. So as time grows short, I'm going to quickly show you one example of a question that probably has no answer. And it's a question that came up in my own research. So I've put down two other questions, but the question I want to focus on is this. Is the dynamical system, x goes to x squared minus c, chaotic for c equals 1.5? Okay, now you're probably asking yourself, what does chaotic mean? And you should be. So what is chaos?
An antonym of order. Harvard's Curtis McMullen studies its theory.
What is chaos?
Chaos is the word, yes.
So this is the closest I've come to actual fame in my life. Apparently what I study is called chaos theory. So let me try to make it a little more precise for you. So here's the toy model. I have a new investment, and when you give me your money, I promise that next year I'm not going to double it or triple it. I'm going to hand you back the square of what you gave me. Pretty good, right? So you give me $10 next year, I'll give you back $100. After that, $10,000, and so on. The only thing is I'm going to take off a small commission. See, okay? But you'll still get the rest back. So you wisely decide to invest nothing. And if my commission is 0, then nothing happens. Your account just remains at 0. However, what if I charge $1 commission? What happens is the first year you go into debt. You have -1 in your account, but luckily the square of a negative number is positive. So now you earn $1 the next year. Oh, but that just cancels out my commission. And now you go back into debt again. So you're in this cycle of 0 and -1 in your account, but at least you get back to 0 infinitely often. On the other hand, what if I decide, wow, I'm making a lot of money, I'll make the commission really high, what about I'll make it 3? Well, then you go into debt by $3 the first year, but then you get 6 the next year because this squares to 9, and then I take off 3, and then this squares to 36, I take off 3, and you have a runaway super good investment. So this shifting pattern of evolution, the way this changes as the commission changes, that's what dynamical systems is about. And it turns out that if we study as the commission increases, what happens to the balance in your account, what we find is that when C is small, your account tends to converge to some stable number. But when C gets larger, it goes into these alternating cycles of boom and bust. We saw one of those. And then those split into cycles of order 4 and order 8 and so on. And then eventually chaos ensues. So once the driving number C is large enough, you go through this cascade of period doublings and arrive at something where the behavior of the money in your account becomes kind of unpredictable. You know, you've lost the stability of your investment. And then there's all this mess up here where we have strange attractors. That's called chaos theory, where it's hard to predict where your account will be 100 years from now. But oddly enough, there's some little eye in the storm farther up, and also some little strange feature in the eye of the storm. And if we zoom in on that, what we see is a recapitulation of the whole story again. So in fact, within this chaotic regime, there are very tiny windows of order that we might happen to land in. And so the question we might ask is, what if we make the commission exactly 1.5? Is this arrow pointing towards one of those tiny windows? Or is it pointing into this chaotic regime where everything is fairly dark? And what happens experimentally is you zoom in on this picture more and more, and the windows get narrower and narrower, and you don't seem to be pointing into one. But it might be that you're just off a little bit. And if you move the arrow up just slightly, in fact, you are in a window. And how will you ever know the difference? And the reason this question probably has no answer is that this picture doesn't know anything about rational numbers. And so the fact that this happens to have a simple decimal expansion has nothing to do with the behavior that ensues here. And there may be no way to logically deduce from this description of C what actually happens dynamically. Okay, so we have to live with that. We can't answer every question. There is an ignorabilis in mathematics. It might not be this, but Gödel predicted that there will always be questions we can't answer. Okay, I can live with that, but it turns out one of the questions we can't answer is even worse. Is mathematics consistent? In other words, if we adopt Hilbert's axioms and then we start proving theorems, is it possible that we start making deductions about what's true and what's not true, and then we come to a contradiction? We think that this number is even, and we think the red numbers are odd, and then we get a number which is neither odd nor even. Maybe we can write down a proof that 0 is equal to 1. Maybe our entire mathematical system is about to collapse. Maybe it still suffers from the paradoxes of infinity. And what Gödel proved is that we'll never know the answer to this question. So here's what I encourage you to do. First, think about the whole numbers. A lot of people have said, look, don't worry about it. We know that the whole numbers exist. At least the mathematics we're proving about 0, 1, 2 is not wrong. In fact, Kronecker said, God made the integers. All else is the work of man. As long as we stay away from the work of man, we're probably safe. Here's a modern response. Nelson in 2010. The notion of the actual infinity of all numbers is a product of human imagination. The story is simply made up. Why should we believe that God made the integers? How long did it take? So he writes, the tale of the natural numbers even has the structure of a traditional fairy tale. Once upon a time, there was a number called 0. It had a successor called 1, which in turn had a successor called 2, and all the successors had successors happily ever after that. The belief that exponentiation, superexponentiation, and so forth, in other words, these towers and wowzers, applied to numerals yields meaningful numerals is just that, a belief. Wow. So Nelson encourages us to doubt the existence of the integers themselves. Okay, now here's the perspective you could adopt if you're willing to be a real skeptic. Maybe there is a proof that 0 equals 1. Okay, that's fine. I'm going to call n the length of the shortest proof that 0 equals 1. That's the size of the mathematical universe. Don't make proofs longer than that. You may run into trouble. What is wrong with imagining that there's an enormous quantity which plays the role of the diameter of our mathematical universe, and that its reciprocal is the analog of the Planck constant in physics? Maybe mathematics should be treated skeptically. Maybe it has its own built-in limitations. And what Nelson showed, remarkably, is that if you're willing to imagine that mathematics may be inconsistent, then you get a new way of looking at the whole numbers, which is to your advantage. Namely, here's the fairy tale, 0, 1, 2, etc. And then here's this non-standard number. You better not go this far. This is where you can prove 0 is equal to 1. He says, let's imagine that you can't see these numbers unless you put on rose-colored glasses. When you put them on, you can see them. They're called non-standard. These are called standard, but most of the time, we don't look at them. And then we have the following axioms for mathematics. Everything that we thought was true before is still true. 0 is a standard number. When n is standard, n plus 1 is standard, but we assume there exists some number which is not standard. Why not be skeptical? And it turns out if you admit the existence of this non-standard number, a lot of good things happen. First, Newton is rehabilitated, the paradoxes of Cantor go away, and analysis is simplified. Let me say what this means. Suppose we have one of these non-standard numbers. You should think of it as being a very big number, for all practical purposes infinite, but not actually infinite. Then 1 over n works perfectly well as an infinitesimal, and you can build calculus without this mantra of epsilons and deltas. What about all this stuff about infinity? You don't need infinity anymore. Working with very, very large finite sets whose number of elements is this enormous number n, it is just as good as working with infinite sets. So all the complexities of analysis and measure theory go away. And in fact, Nelson, using these axioms, wrote a book called Radically Elementary Probability Theory, which was actually much simpler than any previous text on probability theory. It just rested on different logical foundations. Okay, so where do things stand? Here are the possibilities. Think of what we now know in physics. There's something called the vacuum. It's supposed to be empty space. It's not empty. It's full of virtual particles. How is empty space filled with virtual particles? It's because they break the rules of physics. The uncertainty principle allows particles to come into existence and disappear as long as they do it fast enough that we can't see them. Okay, but that's just a theory, right? No, 70% of the universe is made up of these inconsistencies. This is one of the most popular models for dark energy. Dark energy consists of violations of the rules of physics at a scale that's so small that we can't ever observe it. That's called dark energy. There's our universe. Little contradictions everywhere. So let's remember that mathematics itself is a model. Which model of mathematics best fits with the world as we now know it? Is it the model where we blindly believe in these towers of tens as actually representing numerals? And if so, if you're willing to admit such enormous numbers, maybe you are also willing to accept or at least entertain the possibility that we are living in a bubble of virtual logic, which appears to be consistent because of the enormously tiny and humbling fraction of the bubble needed to support the physical universe and ourselves within it. Thank you.
Hello? All right. Are there any questions?
So what about the continuum hypothesis? That the continuum is...
So the question was, what about the continuum hypothesis? So this is I don't want to get too technical here, but this went flying by on a slide when I realized I started late, but was nevertheless running out of time. The continuum hypothesis is a specific example of a mathematical question that has been proved to have no answer. The axioms that we now have are consistent with this hypothesis being true and with it being false. So I gave an example of what I thought might be a question we can't answer. It's an example of something we definitely can't answer. That's how it fits into the picture.
Maybe one more question.
If my memory doesn't fail me, I think I read that there's a palimpsest from Pythagoras where people think that he actually came up with calculus. Do you know anything about that?
Unfortunately, I don't. I'm skeptical, but I'm skeptical about a lot of things.
Let's thank the speaker one more time.